Hi, we're going to continue our discussions around ions. Specifically, today we're going to learn how to name ionic bonds with monoatomic ions. We'll talk about what that means, and we're going to be able to give the formulas for them. Before we get into that, let's just review what an ion is. An ion is a charged element. And there's two types of ions we can have. We can have a cation, which is a positively charged element. Remember, cats have paws. So cations are positive. And we also have something called an anion, which is just the opposite. It's a negatively charged element. And cations form by losing electrons. Remember, it's the opposite. When we lose electrons, we become positive, and anions form by gaining electrons. Okay, we can't change the number of protons. We can only change the number of electrons. Protons give identity to the element. If we change the number of protons, we've changed the element, but we can change the number of electrons to add stability. But the question is, why does this happen? Why do elements gain and lose electrons? Gain and lose electrons, not elements. But why do they do this? They do this because they want to fill the outermost energy level. By fill, we mean we want the s orbital to have 2 electrons, and we want the p orbital to have 6 electrons. That together equals 8. We learned last time that all electrons want 8 electrons. It's the octet rule. We say that simply, but it's because the outer shell of the electron will be completely full, and they can't remove or gain electrons. We should know how to find the number of valence electrons to basically tell us what the ion of an element will be, but if we pull up a periodic table, I can review that. Everything in group 1 will have a +1 charge, has 1 valence electron, we remove it, that will give us a +1 charge. Same thing with group 2, except they have 2 valence electrons. So we remove 2, that'll give us a +2. And then group 13 will be +3. We'll talk about the transition metals towards the end of the lesson. Remember that group 14, carbon, silicon, germanium, tin, these don't form ions. It's like that awkward number where do they gain 4 or do they lose 4? So they don't form ionic bonds, they form something called covalent bonds, which we'll talk about when we get back from Thanksgiving. And on the opposite side of the periodic table, we can say that everything in group 15 has 5 valence electrons. We're going to add 3 to get to 8, so that's a -3 charge. And basically the same reasoning for group 16 and 17, except it's -2 and -1. The noble gases or group 18, are really special because they already have a filled shell. So it would make no sense for them to already have filled energy levels. So it wouldn't make sense for them to gain or lose electrons when they're already at the sort of ideal state. We'll refer back to the periodic table as we kind of go through this lesson too. Today we're talking specifically about monoatomic ions. The word mono means 1. Atomic just means atom. And we know that ion now means charge. So basically what we're looking at are singular elements that have a charge. And based on what we just did, most elements have a specific charge or an ideal charge that they want to get to. Cool. Now, the whole point today is we're going to form what's called ionic bonds. Okay. So when an element, let's just use the element barium. Barium has 2 valence electrons. When we get rid of those electrons to give it a full shell, we have to now signify or write down that barium now has a +2 charge. Okay. On the opposite side, if we look at something like oxygen, oxygen has 6 valence electrons. If we add 2 valence electrons to that, we're going to end up with 8, but we have to sort of write down a way that we can show that, so we put a -2 charge next to oxygen. And we should know how to do this. It should kind of make sense now that the 2 valence electrons from barium are actually going to be donated or transferred to oxygen, since they need that. They need to get rid of, one element needs to get rid of the electrons, one element needs to gain electrons, so it just makes sense in this way. But why I'm saying this is because when we have a charge, we have a form of electrostatic attraction or electrodynamic attraction. When we have a positive charge, that's going to want to get really close to the negative charge. So it's not like they're like connected by some kind of string. They're connected by literally forces of the positive charge to the negative charge, which is the reasoning behind why these elements want to come together and form bonds. Now, there's 2 things that we're going to want to do with this. We're going to want to name ionic bonds, and we're going to want to give the formula for an ionic bond. And you'll have to know one to know the other, unless it's like a riddle of sorts. But the formula for the names, the way that we name is we always put the cation before the anion. So whichever one has the positive charge is going to be named first. Okay? And really important, the name stays the same. Name stays the same. Okay? The anion is the negatively charged ion, and it's almost named exactly the same. We just changed the ending to IDE. So the suffix will change. Instead of it being like oxygen, it'll be oxide. And again, I think once we do some examples, it'll make a little bit more sense. The formula, all you need to know for the formula is that the charges need to balance. This requires some math, but it's really basic addition and subtraction. Let's look at an example. And again, these are all monoatomic elements, so we can just grab them from the periodic table. Let's look at our first one where we had barium 2+ and oxygen 2-. Okay? These charges already cancel them out, so our formula is going to be just BaO. If we want to name it, we always put the cation first, which is barium, and then we write the anion second, but we change the ending to IDE. Sometimes these can be a little bit tricky, like oxygen, for example. Why is it not oxygenide? I think it's just a sort of flow, but most of them are pretty, are things that we've maybe heard before too. So let's do some examples of just naming. Let's do KBR, SR3N2, RB3P, 4LICL, and then let's do number 5, CS2O. We'll talk about these subscripts in just a second. Most, if not all, ionic bonds will have a clear separation between both elements. And then we just take the cation. So for the first one, we have K. We don't change the name of the cation, so it's potassium. And then we have bromine on the periodic table. But again, instead of writing bromine, we change the ending to IDE, so it's bromide. The next one, I know there's a 3 and a 2. Again, we'll talk about that in a second. But the SR on the periodic table is just strontium. Don't change the name. And then we have nitrogen, so it's nitride. Can also do the same thing for rubidium, phosphide, lithium chloride, and then the last one we have cesium oxide. Cool. Going from formula to name, I think is a little bit simpler than going from the name to the formula. Okay. Again, if you're given the name, our goal is to balance out charges. There's kind of two ways that we can do this. But let's look at something like sodium chloride. We know sodium, we know chlorine. If we look at the periodic table, sodium has a +1 charge. Chlorine has a -1 charge. Our charges are already balanced out, meaning that we don't even have to do any math. They add up to 0, they balance. It's just NaCl. Same thing if we had something like calcium and sulfur. Calcium is 2+, sulfur is 2-. They already balance out, so we have CaS, calcium sulfide. And if we want to be even more, if we want to go even more in depth and do ions that have a +3 and -3, we can do aluminum and phosphorus. Again, charge is balanced. It's a 1-to-1 ratio of charge. It's AlP. Where it gets a little bit tricky is if these charges are not the same. How do we still balance that out? Okay. Let's look at something like lithium nitride. Okay. If we look at the periodic table, lithium has a +1 charge. It has 1 valence electron. Instead of adding 7, we just remove 1. And let's look at something, let's also look at nitrogen. Nitrogen has 5 valence electrons. Instead of removing those 5, we add 3, just go with the smaller number. Again, these charges don't add up to 0. We have +1, -3, that goes to -2. We need them to balance. The way that we do this, you can use 2 methods. You can use the greatest common factor. So the greatest common factor between +1 and -3 is actually 3. We would just need 3 +1s to do that. Okay, so +1 +1 +1 equals plus 3, that then balances out with minus 3. It's kind of a 3-to-1 ratio, which means we need 3 lithiums for every 1 nitrogen. And the way that we write this is we still write the element symbol, same way that we do this, but we need to count that there's 3 lithiums. So we're going to put as a subscript next to lithium 3. And we don't need to put a subscript for nitrogen because there's only 1. The second way that you can do this is you can write both ions the same way that we would normally do if we're comparing with their charges. So lithium's +1, nitrogen's -3. And you can make sort of like, I usually circle both the charges and make like a happy face, and I switch them, okay? What you do at this point is you take the 3 from nitrogen and you put it as the subscript for lithium, and you'll take the charge for lithium and you'll put it as the subscript for nitrogen. In this case, it's 1, so we don't have to do that. Cool. A lot of people really like this method. I usually call it the happy face method, even though it looks like a bunch of scribbles. But either one that you choose, as long as the charges balance out, if you know another way to do it, or if it just kind of clicks for you, you don't have to use any of these methods. Eventually, we should be able to do this pretty quickly. Let's do some examples where I give you the name and you give me, or we give each other the formula. So if the name is magnesium bromide, let's do that. Let me just write down all the names actually. Let's do barium arsenide. And let's do gallium selenide. I'm gonna move this over a little bit. Cool. Magnesium is +2. Bromine is -1. Again, we can use the method where I put the subscripts I put the charges as the subscripts, so it'll be MgBr2. Or we can understand that we need 2 bromines to get a -2 charge for every 1 magnesium. Barium also has a +2 charge. Arsenic has a 3- charge. Again, the greatest common factor within these two would be 6. So we would need 3 bariums to get to +6, and we would need 2 arsenics to get to -6. Notice here that even though it's Ba3, Ar2, it's still barium arsenide. We don't have to include any of the numbers in the name, because the name already suggests that barium's +2, arsenide's -3. So the only correct formula would be to balance that out. So Ba3, Ar2. Last one, we have gallium, which is +3. And we have selenium, which is -2-. So kind of same explanation. I'll just use the happy face method. I'm going to put the charge of selenium as the subscript for gallium and the charge for gallium as the subscript for selenium. That gives us Ga2Se3. Again, formulas are just the element symbol with the subscript if there's one necessary, and the name is just the cation first, the anion, we change the ending to IDE. Now, one thing that we want to, before we end, is this idea of what if we have transition metals in our name or formula? We haven't really talked about those in terms of ions. We know that they all have 2 valence electrons, but because they have a d orbital, that d orbital has space for up to 10 electrons. So even if we're in the 4th energy level, we still have an empty d orbital. In that case, that can hold up to 10 electrons. So transition metals can have a charge of +1 all the way to +10. And not all of them have every single charge, but it's kind of a good description of, you know, how many charges they can have. It all just varies. We name transition metals the exact same. Oh, sorry, let me pull up a periodic table so that I can show you. Transition metals are this block in here. And remember that we don't account for the lanthanides and actinides. But all of these can have a +1 to +10. It's kind of unknown. If you're given a transition metal, you should know that because it's always going to be +1 to +10, it's always the cation. Okay? So it's always going to come first, so we never have to change the name. Let's look at something like manganese. Okay. Manganese, the charge is unknown, but we know it's somewhere between +1 and +10. Now, if you see something like MnO, or manganese oxide, this actually tells us a lot. Because manganese is bonded to oxygen. We know oxygen has a -2 charge. That's in this group on the periodic table, which means that manganese has to have a +2 charge because it's a 1-to-1 ratio. Whatever the charge is on oxygen needs to be the charge on manganese. So we would call this manganese oxide. Okay. But in the middle, we need to signify that it's a +2 charge. So we write 2 in Roman numerals, and I can go over the Roman numerals. Let's say we had something that was Mn2O. Okay. The charge of oxygen is known, it's -2. We have 2 manganese, so each manganese must be +1, because +1 is going to add up to +2. Okay, so now we can write manganese 1 oxide. And again, these parentheses just tell us what the charge is. Cool? Let's do one more example. Let's do something like ruthenium arsenide. Right, let's do like ruthenium 3 arsenide. And just for fun, let's do ruthenium 5 arsenide. How do we write the formula for this? Well, we know the charge on ruthenium is +3 because that's what it says. This ruthenium is +5. Arsenide is -3. Arsenide is -3. So this, we have a 1-to-1 ratio, so we could just write RuAs. For ruthenium 5 arsenide, this is a little bit tricky. What we can do is just use a little happy face. The 5 is going to go to arsenide. The 3 is going to go to ruthenium. So we have Ru3As5. Okay, so it's just a little introduction to monoatomic compounds, monoatomic ions, sorry. in the next video or in the next class, you're gonna have another video talking about polyatomic ions. Thank you.